Today I want to pick up a question that many of you ask, which is, how do black holes destroy information and why is that a problem? I will not explain here what a black hole is or how we know that black holes exist. For this you can watch my earlier video. Let me instead get right to black hole information loss. To understand the problem, you first need to know the mathematics that we use for our theories in physics. These theories all have two ingredients. First, there's something called the state of a system. That's a complete description of whatever you want to make a prediction for. In a classical theory, that's one which is not quantized, the state would be, for example, the positions and velocities of the particles. To describe the state in a quantum theory, you would instead take the wave functions. The second ingredient to the current theories is a dynamical law, which is also often called an evolution equation. This has nothing to do with Darwinian evolution. Evolution here just means that this is an equation which tells you how the state changes from one moment of time to the next. So if I give you a state at any one time, you can use the evolution equation to compute the state at any other time. The important thing is that all evolution equations that we know of are time reversible. This means it never happens that two states that differ at an initial time will become identical states at a later time. If there was so, then at the later time you wouldn't know where you started from, and that would not be reversible. A confusion that I frequently encounter is that between time reversibility and time reversal invariance. These are not the same things. Time reversible just means that you can run a process backwards. Time reversal invariance, on the other hand, means it will look the same if you run it backwards. In the following, I'm talking about time reversibility, not time reversal invariance. Now, all fundamental evolution equations in physics are time reversible. But this time reversibility is in many cases entirely theoretical because of entropy increase. If the entropy of a system increases, this means that if you wanted to reverse the time evolution, you would have to arrange the initial state very, very precisely, more precisely than is humanly possible. Therefore, many processes which are time reversible in principle are for all practical purposes irreversible. Think of mixing dirt. You'll never be able to unmix it in practice. But if only you could arrange precisely enough the position of each single atom, you could very well unmix the dirt. The same goes for burning a piece of paper. Irreversible in practice, but in principle, if you only knew precisely enough the details of the smoke and the ashes, you could reverse it. The evolution equation of quantum mechanics is called the Schrödinger equation, and it is just as time reversible as the evolution equation of classical physics. Quantum mechanics, however, has an additional equation which describes the measurement process, and this equation is not time reversible. The reason it's not time reversible is that you can have different states that, when measured, give you the same measurement outcome. So if you only know the outcome of the measurement, you cannot tell what was the original state. Let us come to black holes then. The defining property of a black hole is the horizon, which is a one-way surface. You can only get in, but never get out of a black hole. The horizon does not have substance. It's really just the name for a location in space. Other than that, it's vacuum. But quantum theory tells us that vacuum is not nothing. It is full of particle-antiparticle pairs that are constantly created and destroyed. And in general relativity, the notion of a particle itself depends on the observer, much like the passage of time does. For this reason, what looks like vacuum close by the horizon does not look like vacuum far away from the horizon. And this is just another way of saying that black holes emit radiation. This effect was first derived by Stephen Hawking in the 1970s, and the radiation is therefore called Hawking radiation. It is really important to keep in mind that you get this result by using just the normal quantum theory of matter in the curved space-time of a black hole. You do not need a theory of quantum gravity to derive that black holes radiate. For our purposes, the relevant property of the radiation is that it is completely thermal. It is entirely determined by the total mass, charge, and spin of the black hole. Besides that, it's random. Now, what happens when the black hole radiates is that it loses mass and shrinks. It shrinks until it's entirely gone, and the radiation is the only thing that is left. But if you only have the radiation, then all you know is the mass, charge, and spin of the black hole. You have no idea what formed the black hole originally or what fell in later. Therefore, black hole evaporation is irreversible, because many different initial states will result in the same final state. And this is before you have even made a measurement on the radiation. Such an irreversible process does not fit together with any of the known evolution laws, and that's the problem. If you combine gravity with quantum theory, it seems, you get a result that's inconsistent with the quantum theory you started from. As you have probably noticed, I didn't say anything about information. That's because really the reference to information in black hole information laws is entirely unnecessary and just causes confusion. The problem of black hole information laws really has nothing to do with just exactly what you mean by information. It's just a term that, loosely speaking, says you can't tell from the final state what was the exact initial state. There have been many attempts to solve this problem. Literally thousands of papers have been written about it. I will tell you about the most promising solutions some other time, so don't forget to subscribe.